In today's lecture, I'm going to introduce you to the theoretical basis of different types of spectroscopy. And for some of you, this might be a revision of what you know. But for the sake of everyone, in class, it's important, I go through the theoretical basis or the overarching aspect of all types of spectroscopic techniques. And as you well know, spectroscopic techniques are probably the most prevalent of analytical methods out there. And as such, it's important to understand what they are. Now, remember, spectroscopy is the study of the interaction of light, with chemical specimens or with matter. And it is used, to determine the chemical composition of both atoms as well as molecules. And as such, you can have atomic spectroscopy as well as, molecular spectroscopy, all of it based on the way the atoms or the molecules are gonna perturbate electromagnetic radiation when the light impinges on on those types of materials. Now, it's important to understand the properties of light, and I think all of us do, that light operates or works as its inherent nature is that it's not only a particle, but it also behaves, like a wave. The so-called, particle and wave duality, of light. And so you can determine its energy, based on, these equation where you're thinking of it in terms of a particle, and so it's moving or it propagates, in a quantized form. But also, these particles, propagate in the form of a wave, and as such, you can calculate, the energy of light also based on its frequency. And as you well know, frequency slash, wavelength is a property, of a wave. And so think of it, both as a quanta, or rather as a photon, as a particle, but also that particle is propagating in form of a wave, and as such you can determine its wavelength, or frequency. I think it's important, to remember, that the energy, is proportional to the frequency, and that is the frequency. And the frequency, can be calculated, by taking, the velocity of light divided by the wavelength. Now, as I've mentioned, the electromagnetic radiation or light, therefore, is a continuum, of different energies. And so you can have very high energy type of electromagnetic radiation, meaning it's very, very penetrative, things like the gamma rays, the X-rays and so on. And you can have the optical range, that is ultraviolet radiation, the visible range, as well as the infrared. They are of moderate, energies, and as such, when they impinge on a chemical specimen, the electronic, the electrons, of the molecules or the atoms are gonna transition, from their ground state, to the high energies. Now you can also have, lower energies types of electromagnetic radiation, such as, microwave, radio waves, and so on. And equally, when they impinge, on a chemical specimen, the energy is not strong enough to cause electronic transitions, and instead, you would have things like, rotation of the bonding electrons, and so on. So take note of that. Depending on the energy of the electromagnetic radiation that you are using, different valency, different electrons, are gonna be affected, by those types of electromagnetic radiation. And so based on that, then, you can have all sorts of different types of spectroscopies depending on the energy of the EMR, that impinges on the chemical specimen. If at all you are impinging, the chemical specimen with the gamma ray, it is very, very energetic. It does not only, penetrate the outer electrons, it penetrates the inner electrons, and it gets to the nucleus, and that is what you'll be having. Nuclear, those are the type of transitions, that will be taking place. It's going to be affecting, the particles within the nucleus because it's very, very penetrative. Now, on the other hand, if you tell you've got the X-ray, it's gonna penetrate, and cause the excitation, or even sometimes, the complete ionization of the inner electrons. So take note of that. The X-ray, causes the excitation of the inner electrons because it penetrates, the outermost electrons and gets to the inner electrons. So the kinds of quantum transitions that will be taking place, with the X-ray are the inner electrons. And as we all know, X-ray, is a type of spectroscopy. And so in light of that, and you can tell this is the case, because it's causing, excitation of the inner electrons, X-ray is not useful, as a molecular spectroscopic technique, and it's only useful as an atomic spectroscopic technique, because for a technique, to be used for molecularly, it should be perturbating, the bonding electrons. And remember, the bonding electrons are the electrons that are occupied in the outermost shell, which is that, okay? So X-ray, is only really useful as an atomic spectroscopic technique. Now, if you use the ultraviolet radiation, on the other hand, it's fairly energetic, but it's not energetic enough, to cause the excitation of the inner electrons. And so instead, you'll be exciting, the bonding electrons, which are the outermost electrons. And so as such, it's fairly good, for molecular spectroscopy, because you're actually causing the excitation, of the outermost electrons. Similar to, visible radiation, you cause the perturbation, of the outermost electrons. Now, when you're dealing with the infrared, spectroscopy or the IR, it's not energetic enough, to cause excitation, of the outermost electrons, but instead it causes vibration, of the bonding electrons, causes vibration of the bonding electrons. And as such, is a fairly good technique for molecular spectroscopy, because you are perturbating the bonding electrons due to vibration. Raman scattering, on the other hand, and I'm going to talk about it. What's happening to the electromagnetic radiation is that the specimen scatters the light, and that light is scattered in a quantized form, and as such, is fairly useful, for analyzing the molecules, because the types of the types of electrons, that are causing the scattering, are the bonding electrons as well. And so in actual fact, infrared is a very complementary technique, to Raman spectroscopy. And we're going to talk about it, later on when we go into the specifics of all these types of spectroscopies. If you look at the microwave, it's not that energetic, and so it just causes, rotation of the bonding electrons, and that generates heat, and that's why we use microwave for heating, different types of molecules and solvents. It's important to remember, actually, that the microwave only is useful in terms of rotating molecules, that have got a dipole moment, meaning if at all you throw something like a hexane, in the microwave and try to heat it up, actually it does not heat up because the bonds, the single C bond really doesn't have a dipole moment, and so you do not generate, heat. And so it's microwave inactive because you need a dipole moment, for heat to be generated by a microwave. So take note of that. I think what I'm trying to summarize is all the different types of spectroscopies are totally dependent, on which type of energy of the electromagnetic radiation impinges, on the molecule or an atom, and as such that determines, what types of electrons are undergoing transition or undergoing, perturbation. Now, it's important, for me to remind you of a couple of different behavior, of electromagnetic radiation, which is very, very important, because it determines different types of, spectroscopies in terms of the usefulness of, that behavior. For example, we all know, when you take electromagnetic radiation and try to impinge it on a grooved environment, it tends to diffract, it tends to split into its component wavelengths. So if you take electromagnetic radiation and you have it impinge on a groove or a very rough surface, then, it actually splits into its component wavelengths, to sort of form a rainbow. And that is called diffraction. Now, similarly, diffraction can be explained if you take electromagnetic radiation and have it trying to pass through a very, very small, exit slit, like a hole. And because of that, again, you get, the light splitting, into its component wavelengths. And that is what you refer to as diffraction. Now, diffraction, as a form of interaction between, a chemical specimen or a material, with electromagnetic radiation is very, very important in spectroscopy because actually the basis of what you refer to as X-ray diffraction. Now, this is very useful, I guess, for those of you interested, say, in geology, because it's typically used, to try and determine the authenticity, of different types of geological materials or different types of crystals. So if at all I had a crystal, say of diamond, a crystal of, of a different specimen, I can shine light onto that crystal. And we know a crystals, typically is layered, in form of crystal lattices. And because of that, light is going to penetrate, some of these crystal lattices. And because there is an interface, between the crystal lattices, you're going to get some of the light actually being diffracted. And based on that, you can tell, the band gap, the size, of the crystal lattices, which is dependent, on the type of material, the type of crystal it is. And so X-ray diffraction, very, very important, when you're trying to authenticate, different types of crystal structures or different types of geological materials. So very useful, spectroscopic technique, based on, that behavior of light, called diffraction. Now, diffraction is also very useful, in terms of making different types of components that are used in spectroscopy. Now, for example, and we're going to talk about this in detail a little later, when you're doing atomic, say, absorption spectroscopy, you typically need, a monochromator. And most monochromators, the dispersive element in a monochromator is based on what you refer to as a grating. And a grating is just this, a very rough, reflective, surface, where light, can impinge on that very reflective but rough surface and that causes, the diffraction of light into its component wavelengths, and that way you can actually separate, white light, into monochromatic light. And so very, very important component in all spectroscopy, you need a grating, and a grating is based on the diffraction technique. Now, another interesting thing, just to show you the varied, application of this behavior of light, diffraction, is if you take something like, a peacock, for example, and the very radiant colors that you get from a peacock, actually it's based on diffraction of light, because the peacock layers on the feathers, behave like what you refer to as a photonic crystal. And a photonic crystal is not very different, really, from a crystal, from a crystal lattice, where you've got the layers of the feathers of this bird, and they are layered in a very, very specific way, such that light, penetrates, those layers, and at the interfaces, you get light diffracting. And that diffraction really is also dependent, on the angle at which the light, the incident beam of light, impinges, on the layers of the peacock feathers. And that is what you refer to as, photonic crystals. Now, in fact, these days people are trying, to develop what they are calling, smart paints, that are based on photonic crystals. Instead of using chromophores, like dyes and so on, you can actually use plastics or polymers and just simply layer them, very differently, very similar actually to what one of the students talked about, the molecularly imprinted polymers, where you can actually have, a core, and then you layer the polymers in thin forms, and because of that, the light can hit, those films, and at the interface you get diffraction. And so based on that, you can actually get different types of colors. And the good thing, with photonic crystals is that you don't, unlike chromophores, where you need to keep repainting, because the intensity of the color, get bleached over time, as the paint is being exposed to the environment, with the oxidation and so on. With these photonic crystals, the smart paints, essentially you don't need to repaint it. It's a very cool, type of technique that is being used out there, and very, very new in terms of making what they call smart paints. And as such, it can also be used, for making solar panels and so forth. Different type of an application. Now, other than diffraction, we also know that electromagnetic radiation, when it impinges on a material, say you've got light coming from air and impinging on glass, we know the velocity, of light, is dependent, on the refractive index of the material that it is trying to penetrate through. And as such, we know that light changes its velocity when it gets into a fairly dense material, such as glass. And so light actually bends, when it's getting penetrating, a dense material. And the angle at which it actually bends is dependent on what you refer to as, the refractive index, of a material. And as such, you can actually use this technique, to actually determine, the refractive index. Very important, a property or characteristic, of material. In fact, that's what people use to identify, different types of materials, their refractive index, because it's a very, very specific, so you can see again refraction behavior of electromagnetic radiation as it impinges on a material can actually be used for qualitative, analysis, of different or qualitative characterization, of different types of materials so that you can determine, its refractive index and as such, its authenticity. So very, very important, type of application. And it's based on, this relationship called the Snell's law, where the sine theta, that is the incident angle, at which the light is shown on the material, and this one, the sine theta 2, is the angle, at which the light, leaves the dense material, and the others are the relative, the ratio of the refractive index, of material 1 and the refractive index, of material 2. And of course, the refractive index, of AI is known, and so you can actually determine the refractive index of the material that you're shining light through based on the Snell's law. And so you can see that usefulness, of refraction as a very important, behavior of electromagnetic radiation. And so this slide just shows you, different types of refractive indices, of different types of materials. Again, just to show you the importance, of determining the authenticity or qualitatively characterizing materials, just purely based on that simple technique of refraction. Now, refraction, now, another important, type of behavior of electromagnetic radiation, and it's very similar to refraction, is what you refer to as, dispersion. Okay, and again, dispersion, is totally dependent, on the refractive index, of the substance. Now, there are two types of dispersions. When you shine light, onto an object, and the refractive index, as the refractive index increases, you get an increase, in the frequency, of that, of the light, or a decrease, in the wavelength. That is what you refer to as, the normal dispersion, which is shown here, in a typical dispersion curve, meaning the regions where as the refractive index of the material increases, the frequency of the light, also, increases, or the wavelength, actually decreases. So that is what you refer to as a normal dispersion. On the other hand, you can have materials, that have got anomalous dispersion, where the frequency range, changes radically, with the wavelength, and the relationship actually is not quite linear. It's not quite linearly increasing. And so that is what you refer to as, anomalous dispersion. And so depending on the type of material or how light is behaving, for that type of material, you can actually use it, as a component, in spectroscopy. For example, the normal dispersion behavior, is best used, for lenses. And of course, you're going to see lenses are critical components to use, in spectroscopy. Now, on the other hand, when you've got anomalous dispersion, they tend to be very, very good components to use as monochromators, as dispersive elements, in monochromators, because again, you want that radical, change in the frequency so that you can actually get a split, of white light, into its component wavelength. So please take note of that. For normal dispersion, that's the relationship. Refractive index increases as the wavelength decreases, and it's best, for lenses. Because in that case, you've got the chromatic aberrations being minimized. So for your eyeglasses, for example, you want your lenses, to have this behavior of normal dispersion, Otherwise, your sight, is gonna, or your view is gonna be fairly blurry. Whereas when you're dealing with, materials that you want to use as a grating or a prism, or for dispersive of light into its component wavelengths, you want them to have this behavior of anomalous dispersion, where you've got a very radical change, in frequency, due to change in the refractive index. Now, another important, behavior of light, as it impedes materials, is what you refer to as reflection. And reflection often happens, at interfaces, between two different, materials. And I think reflection is fairly common, especially for mirrors, and so on. And you're going to see, again, it's a very important, property, especially for components such as gratings or even lasers, where you want a very reflective surface, so that you get very good transmission of light, from one object, to another. So again, reflection is a very important, premise or property, for different components in spectroscopy. And all of us, I think, know of that relationship, the incident beam and the reflected beam. And again, it's totally dependent, on the refractive index, of the two surfaces, that you are reflecting light to and from. I think the fourth, type of behavior of light, as it impedes a specimen, is what you refer to as scattering, and I think it's fairly obvious. As an incident beam, impedes on the sample, you would expect, the light, to be scattered, by that specimen. And the scattering really is dependent, of course, on the size of the particle, but it's also dependent, on the chemical composition, on the particle. And so based on that, you can have up to 3 different spectroscopic techniques that are based on this behavior, called scattering. I think most of us, know of nephelometry and turbidimetry, which are 2 techniques, that are used to determine dissolved solids, say in water. And so the way it works is you just take light, you shine light, through the sample in a cuvette. And if at all you've got a lot of dissolved solids in it, of course, you're going to get, light being scattered, the incident beam, being scattered, by the particles that are present in the sample. Now, the difference between nepherometry and turbidimetry is actually all based on the positioning, of the detector relative to the incident light source. So if at all you put the detector at right angles, to the light source, that's what you refer to as nephelometry, meaning you'll be detecting, the scattered light. On the other hand, if you are determining, if at all you put the detector at in line, to the incident light source, that is what you refer to as turbidimetry. And you can see it's not very different really, from absorption spectroscopy, because you'll be trying to detect, the transmitted light. Whereas, nephelometry, you're determining actually, the scattered light, and you're not determining, the incident beam. So very important techniques, in determining water quality. Very, very important technique in determining water quality, nephelometry and turbidimetry. And as you can see, they are based on the behavior of light in terms of how it gets scattered, if it hits a specimen. Now, the other type of technique, that is based on scattering is what you refer to as Raman spectroscopy. Now, Raman spectroscopy, is based on, inelastic, scattering of light. And I'll try to explain what that means, in the next slide here. Now, when you take light and you impinge it, on a substance, now you can get, scattering, that is actually quantized, and that is what you refer to as, inelastic. Inelastic meaning, the energy of the incident beam is different, from the energy, that you actually detect. And the difference, is because of electronic transition of electrons, from the ground state, to a higher energy state. So take note of that. With Raman, you're getting, you're doing a quantized, the scattering is resulting into a quantized electronic transition. It's a fairly unique, type of technique. And as I've said, the scattering is inelastic, meaning there is a differential difference, between the energy of the incidence and the energy, that you are determining, in the end. Now, there are two types of, inelastic types of transitions that could be happening, with the Raman. So there's what you refer to as a Stokes shift. And the Stokes shift, is where the energy that is determined, is actually lower, than the incident. Okay? On the other hand, you can have the anti-Stokes. And the anti-Stokes is where you get the energy that is determined in the end. It's higher than the incident beam, that you shown onto the chemical specimen. As you would expect, the probability, of having a Stokes shift is a lot higher than the probability, of having an anti-Stokes shift. Because in almost all cases, the electrons are transitioning from the ground state, to a higher energy level. And then you lose some of the energy, due to radiation-less relaxation, and then, you get the electrons, being transitioning from the higher energy level, to probably the excited vibrational state, of the ground electronic state. And so that way again, you've lost a little bit, of energy because it's landing, in a higher vibrational level of the ground electronic state. And so this one is the more likely event, to happen in most cases. But you have some materials, where you can also get, the anti-Stokes, although the probability is a lot less, where you get the electrons at an excited state, relaxing back, to the ground state and giving you a higher energy. Now, so you're going to see the spectra that typically you get, in Raman spectroscopy. The larger peaks, are what you refer to as the Stokes, because that's higher probability of taking place. And the anti-Stokes, typically it's a much smaller peak, in Raman spectroscopy, because it's unlikely, to actually happen. Now, maybe somebody is going to ask me, what about, the peak, that is right there, that is in between, and it looks, fairly large, compared to the Stokes and the anti-Stokes. This peak is what you refer to as the Rayleigh scattering. Now, the Rayleigh scattering really means, this one is purely, so the energy of the incident beam is exactly equals to, the energy, that you determine in the end. And so it's not very useful analytically, because you didn't get any difference, in the energy. So in the Rayleigh, the energy of the incidence is equals to, the energy, that is scattered. And because those energies are the same, it's not really analytically, useful. However, it happens actually, actually a lot. And so that's why you get to see that peak, the Rayleigh, being fairly large. In fact, the Rayleigh scattering, is the basis, of why you see the sky being blue. Because light, from the sun is being scattered, by the air particles, in the atmosphere. And because of that, you actually see, the light that is scattered in form of the blue hue, that you actually see is because of that scattering or that splitting, really, of radiation into that scattered beam. Now, the last type of behavior of light, that I like to talk about, is polarization. And polarization refers to when you take the plain polarized light, and you shine it on some molecules, especially the enantiomers. The enantiomers tend to rotate plain polarized light, in a certain direction, either right or left. And so based on that, you can differentiate what type of enantiomer or what type of a chiral molecule, is actually present. So it's a very important technique, in organic chemistry, polarimetry, when you're trying to differentiate two types of enantiomers, whether it rotates a plain polarized light, in the left or the right. Now, polarization, is also very common in a technique, that's not too different from polarimetry, called circular dichroism. And this is where you actually measure, the differential absorption of left or light circularly polarized light, as they impede, on a protein. So you can see some proteins, typically, they've got, chirality also in them. And so depending on the direction, at which they rotate, the light, you can actually, differentiate different types of proteins. And that is what, in the y-axis, in this case, for circular dichroism, you are determining, the ellipticity, so meaning the angle, at which the plain polarized light, is being rotated, by the big molecules like the proteins. And so very important technique, again, for characterization, of different types of proteins. And so in the next lecture, we're going to very quickly, now talk about different types of transitions, based on, the physical chemistry, just to quickly remind you, what is exactly happening, to the electronic state, within the molecule, within the atom, when light, impedes, on this, on the atom or the molecule. And as such, that's going to lead us into different types, of techniques, like absorption and fluorescence and so on. That's going to be the next, the next lecture.